The standard procedure of system analysis is based on the direct implementation of the Fourier principle. If it is known how a given linear system reacts to sinusoidal signals of different frequencies, it is also clear how it reacts to all other signals, because all other signals are composed of nothing but sinusoidal signals. This procedure is widely practiced even in school laboratories. The following equipment is necessary: a sine generator and a 2-channel oscilloscope. The properties in the time and frequency domain are to be established by comparing the input and output voltages. Then both signals should be represented simultaneously on the screen. By means of a function generator and oscilloscope, it is possible, using time-consuming measurement procedures, recording the measurement values, and calculating by means of a pocket calculator, to determine the representation of the frequency response according to amplitude and phase between the input and output voltages. For complete and careful measurement with evaluation, you need roughly 2 hours. Here it is accelerated by Daisy Lab. To awaken your enthusiasm for modern computer-based processes, for the same measurement and evaluation with other test signals, and with a much greater degree of precision, you need only a fraction of a second. It is possible to get a quicker overview of the frequency-dependent behavior of the output amplitude by means of the sweep signal. The idea is as follows. Instead of setting the frequency range continuously by hand from the lower starting frequency F start to the upper stop frequency F stop, this is carried out in the instrument by means of a voltage-controlled oscillator. Thus, the circuit is gradually tested with all the frequencies of the frequency range with which we are concerned here. In this illustration, the whole sweep signal is represented on the screen. On the left, the starting frequency, and on the right, the stop frequency. In this way, the curve of the output signal on the screen does not only show the time curve, but also indirectly the frequency response of the system under examination. The time axis is indirectly the frequency axis too. But be careful. Never forget the uncertainty principle. The Fourier transformation of this sweep signal shows the consequences of beginning a signal suddenly, changing rapidly and ending abruptly. In this illustration, the sweep measurement is carried out using band-pass filters by adding low-pass and high-pass filters with different bandwidth, but with the same center frequency. The sweep responses show that in all cases a bandpass was tested. The envelope seems to be somewhat like the transfer function of the bandpasses, but the center frequency seems not to be the same. If we look at the FFT of the sweep response, we see the filter curve of the 3 different bandpasses. Now they have the same center frequency. This shows that the whole information about the bandpass was hidden in the sweep response in the time domain. If the instantaneous frequency of the sweep changes too fast, the uncertainty principle causes that the envelope of the sweep response does not show the frequency response, the transfer function of the system. The consequence of this is there is only one correct path from the time domain to the frequency domain, and vice versa, ft and IFT. In this age of computer-based signal processing, other test signals are gaining in practical significance on account of their theoretical importance, because each theoretical mathematical process can be implemented in a real sense via a certain program algorithm. Other important test signals are delta pulse, step function, burst pulse, noise, Gaussian pulse, Gaussian oscillation pulse, SI function, SI oscillation pulse. How can the oscillation properties of a car, the mass of the car, the springs, the shock absorbers form a strongly damped mechanical bandpass be measured in a straightforward way? Easy, by driving over a pothole in the road at speed. If the car continues vibrating for a longer time, because of the uncertainty principle, UP, it is a narrow band system, the shock absorbers are not in order. That means the car as a mechanical oscillation system is not sufficiently damped. The delta pulse response, generally called the pulse response, provides, via the uncertainty principle, qualitative information on the frequency properties of the system being tested. But it is only the FT that provides precise information on the frequency domain. It alone shows what frequencies and their amplitude and phases the pulse response contains. If a system is tested by a delta pulse, it is, unlike the sweep signal, tested simultaneously with all frequencies, sinusoidal oscillations of the same amplitude. In order to obtain the frequency response, the pulse response must simply undergo an FT. As in the case of the delta pulse, all frequencies have the same amplitude. The amplitude spectrum of the pulse response forms the curve of the absolute value of the transfer function. The importance of the delta pulse as a test signal is based on the fact that the Fourier transformation of the pulse response already represents the frequency response. That means the transfer function of the system tested. The FT of the insignificant looking pulse responses produces, as if by magic, the transfer function according to absolute value and phase. At the top, you see the pulse responses and frequency responses of 3 low-pass filters. In the middle, those from 2 high-pass filters, and at the bottom those from 2 bandpass filters. With some training and knowledge, the pulse responses show directly the type and quality of the filter. The disadvantages of the delta pulse as a test signal are its low spectral energy and its dangerous pulse level. In addition, the energy distributes itself equally over the entire frequency domain from 0 to infinity. What might an ideal test signal look like? A test signal that has all the advantages of the delta pulse without its disadvantages. Let us try to describe a signal of this kind. The energy of the signal should be confined to the frequency range of the system to be tested. In this range, all the frequencies, as in the case of the delta pulse, should have the same amplitude, so that the Ft directly produces the transfer function. All the frequencies should be present simultaneously, so that, unlike the sweep signal, the system to be tested can respond at the same time to all frequencies. The energy of the test signal should not be put in abruptly or in a very brief space of time, but continuously, so that the system cannot be destroyed. Please note in this connection that as a result of the UP, a limited frequency band signal must have a certain duration, delta t. The maximum value of the test signal cannot be so large that the microelectronics are destroyed. There is a signal which does all these things, and which we are already very familiar with: the SI function and the SI oscillation pulse. Why has it not been used much up to now? Simple. It can only be generated, that means calculated and evaluated, by using a computer. The use of this signal is therefore only realizable with computer-based digital signal processing. The illustration shows the SI function and the SI oscillation pulse are nothing other than a segment cut out from the spectrum of a delta pulse. Here you see the ideal SI test generator. This circuit, which in principle makes us use of the fact that the SI function and the SI oscillation pulse result as frequency segments cut out from the delta pulse. The delta pulse is first transformed into the frequency domain, Ft. If a low-pass signal is required, the frequencies from 0 to the cutoff frequency are cut out. In the case of a bandpass signal, only the relevant section is cut out. The rest of the frequency band is then transformed back into the time domain, Ift. It is now available as a test signal with a precisely defined frequency range. The most exotic test signal is without doubt pure stochastic noise. As shown at the end of Chapter 2, it results from random processes in nature. Such processes can be simulated as desired by the computer, with the result that noise can also be generated by means of the computer. Does noise really contain all the frequencies? This can be checked easily by using our supercircuit. Any 4 frequencies are filtered out in the frequency domain. In this illustration, 32, 128, 512 and 800 Hz from top to bottom. That sounds simple, but at the same time quite amazing. Where do bandpasses exist, whose bandwidth is only 1 Hz? Our filter bank is only limited by the UP. In the case of some test signals, such as delta pulses or step functions, we expose a circuit or a system to a sudden change and observe the reaction. The pulse response and the step response reproduce this reaction. Frequency-selective circuits exhibit a certain temporal delay as a result of the UP. The transient response reflects the reaction of the system to a sudden change in the original condition. It lasts as long as the system is attuned to the change or has reached its so-called stationary state. The transient of a system betrays its oscillatory features in the time and hence in the frequency domain. For this reason, this can be subjected to a systems analysis. During the transition, the system provides information about itself, and then largely conceals the information on the actual signal to be transported from the input to the output. The actual transmission of a signal is restricted essentially to the sphere of the stationary, steady-state condition. In order to achieve a considerable flow of information throughout the system, the transient time delta t should be as short as possible. According to the UP, the bandwidth delta f of the system should be as large as possible.